Acids and Bases, Part 2, pH. In this video, you'll see how to use the pH scale to determine acidity or alkalinity and to perform calculations. You'll also see how to calculate the pH of both strong acids and weak acids. And you'll learn about percent dissociation. In aqueous solutions, the concentrations of hydrogen ions are usually extremely small, but the pH scale provides a more convenient way to represent how acidic or basic a solution is. It is a logarithmic scale based on powers of 10, so a change in pH of 1 is a 10 times change in concentration. For example, orange juice, which has a pH of 3, is actually 10 times more acidic than tomato juice with a pH of 4. Because gastric juice, or stomach acid, has a pH of 1, compared to the pH of tomato juice, gastric juice is 1,000 times more acidic than tomato juice. pH is calculated by taking the negative base 10 log of the hydrogen ion concentration. For example, if a solution has an H plus concentration of 1.0 times 10 to the negative fifth molar, its pH is found by taking the negative log of that concentration. In this case, the pH is 5.00. When dealing with logarithms, the number of decimal places is the number of significant figures, so this pH has two significant figures, as it should based on the concentration it was calculated from. pH isn't the only log-based scale. pOH is the negative log of the hydroxide ion concentration, and pK is the negative log of the equilibrium constant. Let's practice some pH and pOH calculations. What is the pH and the pOH for a 25 degrees Celsius solution with a hydroxide concentration of 1.0 times 10 to the negative third molar? The ion product constant Kw is equal to H plus times OH minus concentrations. By solving for H plus concentration and substituting the given values, we see that H plus concentration ends up as 1.0 times 10 to the negative 11th. The negative log of that concentration is equal to 11.00. The negative log of the hydroxide ion concentration is equal to 3.00. What about the pH and pOH for a 1.0 molar hydrogen ion solution? We can find the hydroxide ion concentration using the ion product constant and the given hydrogen ion concentration. The negative log of each concentration gives us a pH of 0.00. The negative log of the hydroxide ion concentration is equal to 14.00. It is possible to have pH values below 0 and above 14, but most solutions stick within the range of 0 to 14. Perhaps you've noticed the relationship between pH and pOH. We can derive that relationship by starting with the equilibrium expression for the autoionization of water. By taking the negative log of each side of the equation, we find that pKw is equal to pH plus pOH. At 25 degrees, the negative log of Kw is 14, so the sum of pH and pOH is always 14.00 at 25 degrees Celsius. Now that we've covered the basics of pH calculations, we can look at the pH of strong and weak acid solutions. So how do you calculate the pH of a strong acid solution? Let's study this example, a 1.0 molar hydrochloric acid solution. To solve this problem, and any acid-base problem, we need to focus on what molecules and ions are present in solution and which among them are important for determining equilibrium concentrations and thus the pH. This is in fact the most important step in solving any acid-base equilibrium problem. For this example, with hydrochloric acid solution, there is of course a large amount of the solvent, water molecules, present in the solution. Since HCl is a strong acid, virtually no HCl molecules are present because they have completely dissociated into H plus and Cl minus. So the major species in this solution are water, hydrogen, and chloride ions. There are some hydroxide ions present in the solution due to the autoionization of water, but the concentration would be extremely low and insignificant. To figure out the solution's hydrogen ion concentration, we could ignore the contribution from the autoionization of water because it is also negligible compared to the H+ contribution from the acid. Additionally, the H+ contribution from the acid forces the autoionization equilibrium to the left to produce even more water molecules and fewer ions. Since hydrochloric acid is a strong acid, the initial concentration of HCl molecules is the concentration of hydrogen ions. Notice this is a stoichiometry problem, not an equilibrium problem, because HCl is a strong acid. The pH is found from the negative log of 1.0, so the pH is 0.00. What's the pH of 0.10 molar nitric acid solution? To solve this problem, first consider the major species in the solution. This time the major species would be water, hydrogen ions, and nitrate ions. Since the hydrogen ion contribution from the acid is much larger than that from the autoionization of water, the acid's H+ contribution will determine the pH. The strong acid produces 1 mole of hydrogen ion from each mole of nitric acid, so the hydrogen ion concentration of the solution is 0.10 molar. That makes the pH of the 0.10 molar nitric acid solution equal to 1.00. How would you approach solving this problem and calculate the pH of 1.0 times 10 to the negative 10th molar hydrochloric acid? Don't be so hasty that you think that the hydrogen ion concentration would thus be 1.0 times 10 to the negative 10th. That would make the pH 10, and this hydrochloric acid solution would be basic. That doesn't make any sense. Instead, let's approach the problem systematically, just as we have with the past few examples. The major species are water, hydrogen ion, and chloride ion. In this case, the contribution of hydrogen ion from the acid is much lower than the contribution from the autoionization of water. The hydrogen ion concentration then would be 1.0 times 10 to the negative 7th from the autoionization of water. The negative log of that concentration is 7.00. This solution has such a small concentration of hydrochloric acid that it is a neutral solution. Next, we'll apply these same principles to determine the pH of weak acid solutions instead of strong acid solutions. What is the pH of 1.00 molar hydrofluoric acid solution with an acid dissociation constant of 7.2 times 10 to the negative 4th? To solve this problem, we need to focus on the major species in solution, which include water and HF molecules. HF is a weak acid, so it does not completely dissociate. The dissociation equilibrium position will lie far to the left, and acid molecules will predominate. Now we have two species which can produce hydrogen ions in solution. When we compare the acid dissociation constant for HF to the ion product constant for water, we see that the HF dissociation, with the much larger constant, will determine the equilibrium concentration of hydrogen ions and, as a result, the pH of the solution. We know the equilibrium expression and the acid dissociation constant for this reaction. We also know the initial concentration of HF is 1.00 molar, of F- is 0 molar, and for all intents and purposes, of H+ is 0. So how do we determine the equilibrium concentration of hydrogen ions? Well, the same way we solve any equilibrium problem. Let's set up an ice table to display the initial concentrations of each species, predict the change, and explore the equilibrium concentrations. The equilibrium in this reaction must shift to the right, since no fluoride ions are present to shift it to the left. That means that the equilibrium concentrations can be represented in terms of x, the extent of the reaction, as shown here in green. Once we write out the equilibrium expression and substitute our equilibrium concentrations in terms of x, we have an expression that we can solve for the H+ concentration. But we should stop and ask ourselves if the equilibrium constant is small enough to use an approximation to save us some time. This Ka is very small, so the extent of the reaction will also be very small. In essence, the concentration of HF will not change very much, so we can approximate and greatly reduce the amount of time we spend working on the algebra of this problem. We see that X equals 2.7 times 10 to the negative second molar, which is our H plus concentration. Or is it? Before we move on, we should check the validity of our approximation using something called the 5% rule. The 5% rule states that if the extent of the reaction is less than or equal to 5% of the initial acid concentration, then our approximation is valid. We see here that our X is 2.7% of the initial HF concentration, so the approximation we made is good. The hydrogen ion concentration is 2.7 times 10 to the negative second molar. The pH would then be 1.57. This process is the general problem-solving strategy that should be employed when solving weak acid equilibrium problems. Just remember to consider which species are present in solution and which reactions or equilibria will predominate to produce the hydrogen ion concentration that you need to calculate the pH. Percent dissociation, also known as percent ionization, is a measure of how much the weak acid dissociates. It is the ratio of the amount dissociated over the initial amount, times 100 to turn the decimal into a percent. For any given weak acid, the percent dissociation increases as the acid becomes more and more dilute. This means that 0.10 molar acetic acid has a much greater percent dissociation than 1.0 molar acetic acid. This does seem counterintuitive, but let's examine this scenario a little further. For any weak acid solution, as the initial concentration of acid molecules decreases, the concentration of hydrogen ions produced also decreases, but the percent dissociation increases. Consider the reaction quotient for an acid that has reached equilibrium and then has been diluted tenfold. The concentrations at equilibrium would yield this reaction quotient, which is 1/10 of the Ka. Since Q is less than K, this reaction shifts to the right, producing more dissociation, and therefore increasing the percent dissociation for this weak acid. Work through the equilibrium calculations and see for yourself if you don't believe me. Just kidding, we'll probably do that in class for a warm-up. This video has provided instruction regarding the pH scale, calculations of pH for both strong and weak acids, in addition to percent dissociation. If you have difficulties with these concepts, first of all, remember that with practice you can overcome many of these difficulties, but you can also rewatch this video or review the appropriate pages in your textbook. Leave a question in the comments if you like. Thanks for your attention. Next time, we'll move away from acids to focus on their alkaline brethren, the bases.